Hi, my name is Sinickas. I just finished my Masters with Bruce and the ASARC team, where I was looking at the big picture side of avalanches. How do we protect ourselves and our infrastructure against the big or extreme avalanche events? So to give you an idea of what I'm talking about, we can play a game of have you ever. Have you ever driven through Rogers Pass in a huge snowstorm and waited for the plough to pass before going through the snow sheds? Have you ever travelled by train through Europe and looked up at the start zones that are covered in snow fences? Have you ever been so totally stoked on a powder day that you've given the lifty at the Top Shack a high five? Or more importantly, have you ever ate, drunk and been merry at a mountain refugio or hut in the middle of winter? So for those of you who have done any or all of these things, you'd pretty quickly realize that there are two things in common. The first is that they're all desirable life experiences. And the second is that you hope someone intelligent and diligent and trustworthy has made sure that you are protected whilst you're traveling, skiing or eating in these mountain areas. So what do these diligent, responsible people do, these planners and these engineers? Well, say they wanted to design a building in the bottom of a runout zone. To do that with good conscience, they would want to understand how far avalanches run in that avalanche path and how often. The first step of doing that is to try and establish some kind of history. And to do that, you speak to the locals. You go out on site, you cut down trees, and you have a look to see if you can find any evidence of previous avalanches. You then would look at air photos, you'd look at satellite images, you would look at terrain maps, topographic maps and digital terrain maps. And then you might apply some dynamic models. These are models that look at how avalanches flow down a slope. And you would also apply statistical models. Statistical models estimate how far avalanches might run based on, and how often, based on what avalanches in a similar area have done in the past. And that's where our research comes in. We wanted to test or to validate a particular statistical model. The model was created by Professor Dave McClung at the University of British Columbia. For those of you who are tech heads and speak in equation, you can look up his paper. It was published in the year 2000 and it's called Avalanches in Space and Time. For those of you who want more information on the model but are not necessarily tech heads, you can have a look at our paper that was published in the International Snow Science Workshop proceedings from Grenoble in 2013. For anybody else who's interested, the next part of this video will explain how we validated this model. It's called the space-time model. Okay, so what is this space-time model? The space-time model estimates how far avalanches run, or space, using the Gumbel distribution, and models how often they run there, or time, using the Poisson distribution. It always makes more sense for me to see an example, so let's do that. We have a mountain, and we have an avalanche path. To run the model, we need to know a few things. First of all, we need to know a return period and run out distance for one particular point. For example, say we know that at this red dot, the return period is 1 in 3. That means that we expect one avalanche to occur every 3 years. And at this red dot, we also know that the run out distance, meaning the horizontal distance from the start zone to the red dot, is 1,500 meters. The model also requires a few other parameters that are based on the runout ratio model for those of you familiar with statistical modeling. So once we have these parameters and input data, we can estimate the distances to different return periods down the path. For example, we might want to know how far it is to the 10-year line, or how far it is to the 30-year line, or the 300-year line. Sometimes we might be interested in the return period at a particular point, an interesting point, for example, at this house or at a road that runs through the runout zone. So you can see that this model could be very, very useful. We could use it to help us design defense structures. We could use it to help us design lift towers, to work out where we should put our access routes or our highways. We could even use it to help us define between simple and challenging terrain on the avalanche terrain exposure scale, which is being developed by Parks Canada to map terrain. The only problem with this model is that it hasn't been validated yet, and sometimes people are reluctant to use it if they don't know how good it actually is. So those were our objectives. We wanted to work out, does the model work, number one, and number two, does it work differently in different mountain ranges? So how did we set about doing this? Well, we performed 2 independent validations using 2 different sets of data. The first set was vegetation analysis, and the second was historical records. In this video, we'll just look at the vegetation analysis. So over the 2012 summer, we surveyed 34 avalanche paths. And the way that we did that was we walked to the top of the runout zone and we walked down the center line. And each time we recorded where we thought there was a change in return period. So to make it a little bit more obvious, this is a photo that we took from a path just outside of Golden. And we started from where we took the photo and we walked down to this first trim line. And from the vegetation around there, we established a return period of 1 to 3 years. After that, we ploughed our way through the forest, we came to the second trim line, and we established a return period of 15 to 30 years, and then 100 to 300 after that. Now, I really love this photo because it also shows this. I'm not sure if the resolution is good enough there, but that is evidence of logging, and it points to one of the key limitations of our project, which was that it's really hard to distinguish between damage to trees caused by avalanches from damage to trees caused by other events, such as logging, fire, windstorms, floods, animal infestations, animal scratchings, you name it. So after we surveyed the 34 paths, we had between 2 and 6 trim lines within each, and that left us 140 points with which to test the model. So say and to do this, we wanted to get a residual, define a residual. So say this yellow dot is our observed trim line, and once we run the model, we get a blue dot. Well, we defined the residual as the horizontal distance between the two. So if the model was working perfectly, the blue dot would be on top of the yellow dot, and our residual would be equal to 0. So I'm going to show a couple of charts in the next few slides, and it would probably help to take a mental picture of this mountain. Okay. So let's imagine that we have an avalanche, a mountain up here, and we have avalanches starting at the start zone, and they run down through the track and stop at this 0 line. On the horizontal axis here, we have the different return periods, increasing return periods from 2 years all the way out to 300. On the vertical axis, we have the residual. Now you may be wondering, why aren't there any meters? I thought that was a distance measurement. And you would be right, except that we scaled the residuals to account for path length. So a 100 meter residual on a 1,000 meter path would be equal to 0.1. So what can we see from this chart? Well, straight away we can see that most of the residuals fall below this 0 line. What does that mean? Could mean 3 things. Number 1, the model is conservative. Number 2, our validation is biased. And number 3, some combination of both. So what could cause the model to be conservative? Well, it is based on the runout ratio, and the runout ratio has shown to be conservative for flat paths, for short slopes, and for high non-exceedance probabilities. What could cause our validation to be biased? Well, the key idea is that our observation methods might be biased. It's very difficult. There's a lot of uncertainty associated with determining return periods using vegetation damage analysis. You'll recall that our second objective was to try to work out whether or not the model performs differently across mountain ranges. So in the next slide, I'm going to show you the same chart, just split into the Rockies paths and the Columbia's paths. Okay, here it is. We have the residual on the vertical axis and the return periods along the horizontal axis. Straight away you can see we've got excellent results for the Rockies in green and okay results for the Columbias in grey. There are many reasons why this could be happening. If you'd like to read a little bit more about it, please have a look at our paper. Okay, to sum up, the space-time model estimates run-out distances and return periods down the length of a path. It could be really useful in helping planners and engineers decide where to put their infrastructure and how to protect it. We validated the space-time model using two different methods, one using historical records and the other looking at vegetation analysis. And we found that the space-time model estimated run-out distances conservatively, but that it estimated paths within the Rockies very close to what we saw in the field. We hope that this validation gives people more confidence in using the model, but we'd also like to see the validations improved, first by adding more paths to the model, and second by testing it in different regions. Thank you to all of our sponsors. In particular, thank you to our field volunteers who donated each a week of their time to smash around in the undergrowth, and also to the people who provided us really good beta on which study sites to visit and the history of those avalanche paths.